China just spent over $1 billion on glass. You heard that right. Not on transistors, not on lithography machines, on glass. And that single bet may have just made every advanced chip factory on Earth obsolete. Most people have no idea this is even happening. That is exactly why it is the most important story in the chip war right now. And the craziest part is not what China built. It is what China understood that everyone else completely missed. Here is where the story starts, with a war being fought on entirely the wrong battlefield. They're scared of China's glass. For the last several years, Washington has been running what it believes is the perfect strategy. Block China's access to the machines that make advanced chips, starve the supply chain at the source. No machines, no chips, no chips, no AI, no AI, no dominance. Clean, simple, decisive. And on paper, it looks airtight. The machine at the center of that strategy is built by a Dutch company called ASML. Their extreme ultraviolet lithography systems are the only tools on Earth capable of printing the most advanced transistors onto silicon. Each machine weighs as much as 2 fully loaded school buses. Each one costs close to $200 million. That is roughly the price of 17 F-35 fighter jets for a single piece of manufacturing equipment. And there are only a handful of suppliers in the world capable of building even one component inside it. So when the United States pressured the Netherlands into restricting ASML exports to China, the logic was sound. Cut the artery. Watch the patient weaken. Here is what most people never think about though. That strategy only works if advanced transistors are the only path to semiconductor dominance. And China decided, quietly and very deliberately, that they are not. Think of it like this. Imagine you are trying to win a race, and your opponent has locked up the world's only supply of racing tires. Most people would spend years trying to reverse engineer the tire. China looked at the track instead, and then it built a completely different vehicle designed for a completely different surface, one your opponent's tires were never meant to handle. That surface is called advanced packaging, and the vehicle is glass. Now, here is the part that blows people's minds. The most powerful AI chips being built today are not really single chips anymore. They are clusters. Dozens of smaller chips called chiplets wired together on a shared platform called a substrate, designed to behave as one unified processor. The substrate is the foundation everything sits on. It is what connects the chiplets to each other, carries the electrical signals between them, and manages the heat they generate. And right now, that foundation is made of organic material, essentially a very sophisticated form of plastic. China is not trying to out-transistor TSMC. China is trying to replace the floor TSMC's chips are standing on. And that reframes the entire chip war in a single sentence. Because while Washington was guarding the door, China walked around the building entirely. But here is the thing. Understanding why China made this move is one thing. Understanding why that move is so dangerous requires you to see exactly what is happening to those plastic substrates right now and why they are beginning to fail at the worst possible moment in semiconductor history. The dirty secret underneath. Here is something the chip industry does not advertise. The most powerful AI processors ever built are being held together by what is, at its core, a very advanced form of plastic, not metaphorically. Literally. The substrate, the platform every chiplet sits on, the layer that carries signals between processors and routes power through the system, is made from organic resins and fiberglass weaves. Materials that have served the industry well for decades. Materials that were designed for a world where chips were smaller, cooler, and simpler than anything being built today. That world no longer exists. The AI chips driving the current revolution are not small. A single advanced AI processor package today can stretch beyond 8,000 square millimeters. To picture that, lay 4 standard playing cards side by side. That is roughly the surface area you are dealing with. And across that entire surface, there are billions of microscopic connections, all of them communicating simultaneously, all of them generating heat, all of them, depending on the substrate beneath them, staying perfectly, dimensionally still. And here is the brutal catch. It does not stay still. Organic substrates expand and contract with temperature. Every time a chip powers up, heats, then cools back down, the substrate moves. Not visibly, not dramatically. We are talking about shifts, measured in parts per million. But at the scale of modern AI packages, parts per million is not a rounding error. It is a catastrophe waiting to happen. Those microscopic connections, some finer than a strand of human hair, begin to drift, slowly at first, then faster, until the electrical path between two chiplets that was once clean and direct becomes inconsistent, degraded, and eventually broken. Think of it like a suspension bridge in a heat wave. The cables do not snap, they just stretch slightly. But if every measurement in the original design assumed they would never stretch, that slight movement is enough to throw the whole structure out of tolerance. That is what is happening inside the most advanced AI chips on the planet right now. Not a dramatic failure, a slow, invisible drift that engineers can measure, but struggle to stop because the material causing it is baked into every production line, every supply chain, and every manufacturing process the industry has spent 50 years perfecting. Now here is the detail that puts everything into perspective. This problem was manageable when chips were small. It was acceptable when AI workloads were moderate. But the trajectory of AI hardware is pointing in one direction only: larger packages, denser connections, higher power draw, more heat. Every variable that makes organic substrates fail is getting worse at the same time, and the industry knew this was coming. The question was never whether organic substrates would hit their limit. The question was who would have the replacement ready when they did. That replacement has a name, and what it can do defies what most people think is physically possible. What glass actually does. You have almost certainly held the answer in your hand. Not in a chip lab, not in a data center, in your kitchen. A borosilicate glass dish, the kind you bake with, survives dramatic temperature swings without cracking, without warping, without losing its shape. You pull it from a 400-degree oven and set it on a cool countertop, and it holds. That thermal stability is not an accident. It is a property of the material itself. Now, scale that principle down to something thinner than a human fingernail. Engineer it to tolerances so precise they can only be verified under specialized metrology, equipment, and you begin to understand what semiconductor-grade glass substrates actually are. This is not window glass. It is not the glass on your phone screen. It is a purpose-engineered material designed to solve every problem that organic substrates cannot. And the list of things it does better is not marginal, it is structural. Start with thermal stability. Where organic substrates expand and contract with heat cycling, glass holds its dimensional shape with the rigidity of steel. The connections printed onto its surface stay where they were placed through power-up, through full load, through cool-down with no drift, no degradation, no invisible creep pulling chiplets out of alignment. Then there is interconnect density. Today's best organic substrates can support a certain number of electrical connections per square inch before signal interference, and manufacturing tolerances make packing them tighter impossible. Glass supports up to 10 times that density. 10 times. That is the difference between a 2-lane road and a 20-lane highway carrying signals between chiplets at the speeds modern AI demands. Here is what makes this genuinely remarkable. Signal integrity improves at the same time. Organic materials absorb and scatter electrical signals as they travel through the substrate. Glass does not. The signal that enters one side arrives at the other side cleaner, faster, and with less interference, which means chiplets can communicate more reliably without the system having to compensate for degraded signal quality. Now here is the part that most people get wrong about glass substrates. The engineering story is not just about what the material does, it is about what it makes possible. Because once you have a substrate that does not warp, that carries 10 times the connection density, and that keeps signals clean across massive distances, you can build chiplet packages that organic substrates could never support. Packages stretching not just beyond 8,000 square millimeters, but potentially far larger. Packages that let chip designers stop worrying about the substrate failing and start designing for the limits of physics instead. That is the unlock. Not a better chip, a better foundation that makes every chip better. But here is where the story gets complicated, because knowing what glass can do and actually manufacturing it at the scale the semiconductor industry requires are two entirely different problems. And the manufacturing challenge is so brutal, so specific, and so expensive that it has kept nearly every company on Earth from solving it. Nearly every company. But not all of them. The manufacturing nightmare. Picture a drinking straw. Now picture that straw scaled down until it is thinner than a single strand of human hair. Now picture drilling thousands of those straws, perfectly vertical, perfectly parallel, perfectly spaced through a sheet of glass the thickness of a fingernail, without cracking it, without introducing a single invisible fracture that will only reveal itself months later under operating stress. Now picture doing that millions of times per day, at production yields high enough to be commercially viable, with tolerances so tight they can only be confirmed under equipment most companies do not own. That is the through-glass via problem. And it is the reason glass substrates have been theoretically understood for years while remaining commercially out of reach. A via is simply a vertical electrical connection, a channel drilled through a substrate that allows signals to travel from one layer to another. In organic substrates, vias are punched or laser drilled through forgiving, flexible material. Glass is neither forgiving nor flexible. It is rigid, brittle, and punishes imprecision with fractures that propagate invisibly through the material until the substrate fails entirely, sometimes during manufacturing, sometimes during qualification testing, and sometimes, devastatingly, after the finished chip package has already shipped. The drilling itself is only the first problem. The holes must then be filled with conductive metal, typically copper bonded to the glass interior, without introducing stress at the interface. Glass and copper expand at different rates under heat. If that interface is not engineered precisely, thermal cycling creates microscopic separation between the copper fill and the glass wall. The via still looks intact. The signal path still measures clean, until it does not. Here is the detail that engineers do not want to admit publicly. Yield, the percentage of substrates that survive the full manufacturing process without defect, has been the defining problem. Early pilot lines were producing yields so low that the cost per usable substrate made commercial deployment impossible. You cannot build a supply chain on a material that fails more often than it succeeds. Then there is flatness. A glass substrate must be flat to tolerances measured in single-digit micrometers across its entire surface. 1 micrometer is roughly 1/70th the width of a human hair. A substrate that deviates beyond that tolerance cannot be bonded to chiplets with the precision advanced packaging demands. And maintaining that flatness through the heat, chemical exposure, and mechanical handling of a full production process requires process control at a level that took years of dedicated engineering to even approach. Now here is the part that blows people's minds. Even once a company solves yield, even once it solves flatness, even once it proves the process works in a pilot environment, it then has to qualify that process with semiconductor customers. Qualification alone can take 2 to 3 years. During that time, the line generates almost no revenue. The capital is deployed, the engineers are committed, and the market has not yet moved. That combination brutal process complexity, punishing yield challenges, multi-year qualification timelines, and enormous upfront capital requirements is precisely why most Western companies treated glass substrates as a long-term research project rather than an urgent strategic priority. China looked at those barriers and saw something completely different. It saw a moat it could afford to cross before anyone else showed up at the water's edge. And the reason China could cross it faster than anyone expected has almost nothing to do with chips. China's unexpected unfair advantage. Here is what most people get wrong about China's position in the glass substrate race. They assume China is starting from scratch, pouring money into a new technology it has never touched, hoping state investment alone can compress decades of learning into a few years. That framing is wrong. And understanding why it is wrong is the key to understanding why this story is so alarming. China is not starting from scratch. China is redirecting. There is a company called BOE. Most people outside the display industry have never heard of it. Inside the industry, it is impossible to ignore. BOE is one of the largest manufacturers of display glass panels on Earth, the screens in televisions, monitors, tablets, and smartphones. It operates facilities so large that a single BOE campus covers more floor space than many international airports. And to produce display glass at that scale, BOE has spent years building and refining exactly the kind of precision large-format glass handling infrastructure that semiconductor-grade substrate production requires. Think about what that actually means. Precision glass cutting at massive scale. flatness control across large surfaces, high-volume process lines where dimensional tolerances are measured in micrometers, and yield is tracked obsessively because a failed panel at the end of a production line is a direct hit to margin. The equipment categories are different. The end product is different. But the manufacturing discipline, the process philosophy, and the capital infrastructure, those are not different. They are directly transferable. Now here is the part that puts everything into perspective. The semiconductor industry's glass substrate problem is not primarily a material science problem anymore. The physics are understood. The engineering principles are established. The problem is manufacturing specifically, the ability to handle precision glass at high volumes with the process control and yield management that commercial deployment demands. BOE has been solving that exact category of problem at massive scale for years. Not for chips, for screens. But the muscle memory is the same. This is the unfair advantage Western analysts missed entirely. They were watching China's chip fabs. They were tracking wafer starts and lithography tool purchases and advanced node yields. They were not watching the display halls in Chengdu and Hefei, where the industrial capability to pivot into glass substrate production was already humming along at full capacity. And BOE is not the only piece of the puzzle. Chinese companies like Ehint, the TGV division inside WG Tech, and Tongfu Microelectronics have been attacking the through glass via problem directly, the drilling, the filling, the bonding, the yield management with capital and urgency. That only makes sense if the end game is not research publication, but production volume. Here is the brutal catch that makes this more than a manufacturing story. Every one of those companies has been operating with the backing of China's national semiconductor investment funds, the same state apparatus that built SMIC, that scaled BOE, that has a track record of turning strategic priorities into industrial reality, regardless of how long it takes or how much it costs. The West did not miss a research paper. It missed an industrial mobilization. And the money behind that mobilization is larger and more deliberate than almost anyone outside the industry has publicly acknowledged. The billion-dollar bet. Numbers have a way of sounding abstract until you give them a shape. So here is the shape of this one. Since 2023, China's national semiconductor investment funds, combined with direct corporate investment from the companies involved, have directed over $1 billion into glass substrate technology. $1 billion. That is roughly the cost of building and equipping a mid-sized university research campus from the ground up. Deployed not into basic research, but into production-oriented engineering, yield improvement, process qualification, through glass via scaling, and the supply chain infrastructure needed to support commercial volume. And here is what that number tells you, that the number alone does not. Investment at that scale, directed at that specific problem, with that level of state coordination, does not happen because someone found an interesting paper at a conference. It happens because a strategic decision was made at a level above the companies themselves, a decision that said this technology will define the next generation of semiconductor packaging, and China will own it. That decision appears to have been made somewhere around 2022, which means China was placing this bet at the exact moment Western governments were congratulating themselves on the ASML export restrictions. While Washington was locking the front door, Beijing was funding a completely different house being built around the corner. Now here is the part that most people never think about. The $1 billion figure is not the ceiling. It is the foundation. Production lines for glass substrates cost between $500 million and $1 billion each to build and qualify. That means the investment already deployed is enough to have seeded the process learning, but the companies that reach volume production will require multiples of that figure to scale. And in China's model, once the strategic value is proven, the capital follows. Here is what makes this the most time-sensitive story in the chip war. The economics of semiconductor manufacturing reward the first mover in a way that compounds over time and becomes nearly impossible for latecomers to close. It is not just about having the equipment. It is about the process knowledge that accumulates on a production line over months and years of running real material through real tools and solving real problems. That knowledge does not transfer through patents or publications. It lives in the engineers, in the process recipes, In the institutional memory of a team that has seen 10,000 failure modes and learned how to avoid 9,990 of them. Whoever reaches volume production in glass substrates first will accumulate that knowledge first. And the customers who qualify their supply chains against that producer will not switch lightly because requalification costs time, money, and risk that no chip designer wants to absorb without a compelling reason. This is precisely the dynamic that made TSMC untouchable. TSMC did not win because it had better equipment than everyone else forever. It won because it got to volume first, learned faster than anyone else could catch up, and locked in customers whose own roadmaps became dependent on TSMC's process generations. Intel tried to close that gap for 20 years and is still running behind. China understood that dynamic, studied it, and then deliberately replicated the conditions that created it in a market segment its opponents were not defending. But knowing the bet was placed is still not the most alarming part of this story. The most alarming part is what happens to every other player in the industry if China reaches the finish line first, and why the response from Intel, Samsung, TSMC, and Corning tells you everything about how seriously they are now taking a threat they spent years dismissing. The moat is being dug now. Here is what makes this different from every other chapter in the chip war. Most technology races have a catch-up mechanism. A competitor falls behind, studies what the leader built, and closes the gap over time. Painful, expensive, but possible. That is how Korea caught Japan in memory chips. That is how Taiwan caught the United States in logic manufacturing. Glass substrates do not work that way. The moat being built right now is not a technology moat. It is a compounding knowledge moat. The moment any company reaches volume production, every substrate that runs through that line teaches the process something. Every failure mode solved becomes institutional knowledge that cannot be bought, copied, or published. The customer that qualifies against that line builds their next chip generation around its specifications. Their roadmap fuses with the supplier's roadmap, and switching stops being a procurement decision. It becomes a product redesign. That is not a supply chain. That is a dependency, and dependencies of that magnitude define industries for decades. China understood this before the West began paying attention. It placed its bet when the ground was still open, and it is now forcing Intel, Samsung, TSMC, and Corning to respond at a pace none of them originally planned for. Here is the zoom out. The next generation of AI will not be decided by who prints the smallest transistor. It will be decided by who owns the foundation those transistors sit on. Every AI model, every data center, every autonomous system built in the next decade will run on chips. Those chips will run on substrates. And if China owns the substrate, locks in the customers, builds the knowledge moat, then it does not matter who designs the chip. The foundation belongs to Beijing. That is what $1 billion in glass actually bought. Not a product, a position. If this changed how you think about the chip war, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Do you think the West still has time to close this gap, or has China already built a moat that cannot be crossed?